All right, hello. We're going to do section 2.5 today, which is on something called matrix factorization. So here we go. So factorization, that's exactly what you know it to mean, like when you're Algebra 2 class or Algebra 1. Let's say you have a quadratic that you can factor, or let's say you have the number 18 and you're like, oh, let me factor this into like 6 times 3. So when you factor something, you're finding two things that multiply to that item. And so that's exactly what's going to be here too. So we're going to take a matrix like this one right here, and we're going to factor it. We're going to break it into two pieces that multiply back to that item. And so when you do this, there's going to be a special way that it comes about. You're going to have two matrices that you're going to factor it into. One is going to be called a lower matrix, like right here, and one is going to be called an upper matrix, or upper triangular and lower triangular. So this upper triangular one, this is like what you get when you reduce something to like row echelon form. So we're going to do that first, and then we're going to take the identity matrix and go backwards, and we're going to get this one right here. So notice that the upper matrix, it has upper triangular matrix, it has numbers up in the top corner, and usually it can have ones across the diagonal or not. But anyway, this one over here, and it has ones across diagonal, or they might not be, but you have integers down in the corner. All right, so the reason you do this, and if you really want to, you can read on page 142 in your book, and it breaks it into a little bit of a reason why you do this. But when you're trying to solve an equation like ax equals b, and with matrices, oops, that b is kind of ugly. All right, ax equals b. And you know how when we do that, we multiply by the inverse, so we get x equals a negative 1 times b. And so when you find the inverse of a matrix, it involves a lot of steps and a lot of heavy calculations. And so it doesn't seem like it, but apparently it's easier when you're, say, programming a computer to do these things. It's easier to do this factorization way of solving for x instead of finding the inverse and then multiplying it by b. And I know it won't seem like it's less work, but apparently it is. So anyway, here we go. So when we do our row operations here, there's going to be a couple strict things to follow. All right. And so what you want to make sure when you do this by yourself, this first one's done for us, but we're going to reduce the given matrix to echelon form, and we'll do a sequence of operations, but you cannot do row interchanges. So without row interchanges. And then what we're going to do after that is we're going to place entries in the lower matrix in the same sequence of row operations. All right. So and you'll see what that is. So basically our two steps here. All right, so this first one's pretty much done for you. So I'm just going to kind of point to some stuff and you can see what's going on. So you see all these row operations out here. So here's this first one. So it's this original matrix, and then they are multiplying 1/2 times row 1 and getting this new row right here. All right. So on the next one, you have -4 times row 1 plus row 3. It stays in row 3. So I want you to notice something here, and it wasn't written on the last page. So this guy right here, this stays in row 1. Okay. And then here, notice all these row operations. See row 3, row 3, row 2, row 2, row 3, row 3, row 3, row 3. So you're not allowed to interchange anything, and whatever you're putting on the back is where you're staying. So anyway, that's kind of important to do your operations that way. All right, so here's a list of operations, and look what they got right here. This is our upper matrix, just like we were trying to get right here. Okay, all right. So there's our upper matrix. This was our things that we did in this order. Here is the first one, second one, third, fourth, fifth, and so forth. All right. So what they're going to do is go backwards. So all these operations get performed in a reverse order. So it's important to notice what the reverse is. So multiplying by 1/7 times R3, staying in R3, the reverse of that is to multiply by 7. So by reverse, we mean inverse. So the inverse of multiplying by 1/7 is to multiply by 7. And notice that it's R3, R3. Now this guy right here. the inverse of multiplying by 3 is to multiply by -3. And so to do like the opposite in a way, you multiply by -3 and then you notice everything else stays the same right here. And then we get that. And so then up here, this again, -3, row 1, row 2, row 2. So here. And then the next one, -4, changes to +4. And then here and here. So that's all the same. So we're getting this, this new matrix is starting to appear. Right, this one right here. Right, and then finally the last step is 2 times R1. Well, remember, that's because this one right here was 1/2. So basically, if you multiply by something, then you multiply by the reciprocal of it. If you're doing a row addition, then you basically add the opposite of that thing for your reverse order. Right? All right, so we come up with this answer. This is our L. And so what we have now is, if we write those two things down, the original matrix was 2, 6, 2, -3, -8, 0, and 4, 9, 2. And what we have done is we have factored this. It is L times U. So our lower matrix is this one we have, 2, 0, 0, -3, 1, 0, 4, -3, 7, times, and our upper matrix that we had earlier was 1, 3, 1, 0, 1, 3, 0, 0, 1. So if you multiply those back together, you should get the original matrix. And this problem will be used later, so it's good to note that. All right, so we're going to find the LU decomposition of this piece. So we're going to try to find the upper matrix first by doing some row operations. All right, so I think what I'm going to do first is divide or multiply that first row by 1/6. All right, so I'm going to do, let's see if we can write this down, 1/6 row 1. It's going to stay in row 1. Okay, so that will get me 1 and then -1/3 and 0. Okay. Oh, yes. And then my 9, -1 and 1 stays, and my 3, 7, 5 isn't changing. So again, it doesn't matter what order you do this in, you just have to keep track of it. So I did that so that I could get rid of the 9 and the 3. So since these are different rows, I can kind of do it at the same time. So I'm going to multiply, let's see, -9 times row 1 and add it to row 2. It's going to stay in row 2. Then I'm going to do -3 times row 1, add it to row 3 to stay in row 3. Okay, so when I do that, I get 1, -1/3 stays, and 0. The next two rows become 0, 2, 1, and 0, 8, 5. All right, so now, let's see. I think I chose to multiply this guy by 1/2, so 1/2 of row 2 stays in row 2. Okay, and then I'm going to use that to, actually, let's do something else. I changed my mind. Because 2 times 4 is 8, so I'm just going to do that one. I'm going to do -4 times row 2, add it to row 3, and it's going to stay in row 3. Okay, all right, so here we go. So I'm coming up here. I have 1, -1/3, and 0. Then I have 0, 2, 1 still, and now I have 0, 0, 1. Look at that. All right. So now I'm going to do that 1/2. So 1/2 row 2 stays in row 2. So I have 1, -1/3, 0, 0, 1, 1/2, and 0, 0, 1. All right, so there's my upper matrix. Okay, so take note of that, and also basically we want to take note of our row operations, and we're going to go in backwards order. So you have this here, and I'm going to flip the page, and we're going to go ahead and find our lower matrix. All right. Oh. I think, hang on a second. Oh, I was supposed to do that. I need some more space, obviously. I took up too much space. I was writing too big. All right. So anyway, I don't have space there. So let me go ahead and add a page. I will just... oh, well, I added a graph page, so oh well. So let's see, let's add that right there. Okay. All right, so here's my page now. So on my upper matrix, my upper matrix was, I already got that. And so now I need to get my lower matrix. What I'm going to do is I'm going to take the identity matrix. So you take your identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And you go in your reverse order. So the last thing I did was half of row 2 to stay in row 2. So now I'm going to multiply 2 times row 2, and I'm going to stay in row 2. All right, so I have 1, 0, 0, 0, 2, 0, 0, 0, 1. All right, so the next piece, before I had done negative 4 row 2 plus row 3. Now I'm going to do positive 4 row 2 plus row 3 stays in row 3. All right, so I have 1, 0, 0, 0, 2, 0, and then that will be 0, 8, 1. All right, so from here, I have to do 3 row 1 plus row 3 stays in row 3. All right, because remember what I'm doing is I'm going backwards from all these things that I did before, right here. Okay, and so I've accomplished those 3. All right, so when I do that, I have 1, 0, 0, 0, 2, 0, and then finally 3, 8, 1. Okay, all right, so now I have to do 9 row 1 plus row 2 stays in row 2. All right, so I'm going to come up here. All right, so that puts me at 1, 0, 0, 9, 2, 0, and 3, 8, 1. All right, and then the last thing I have to do 6 times row 1 stays in row 1. All right, so I get 6, 0, 0. Then I have my 9, 2, 0, and my 3, 8, 1. So if you go back and check, so this is our L matrix. If you multiply L times U, you will get the original matrix back again. The 6, negative 2, 0, 9, negative 1, 1, and 3, 7, 5. Okay, all right. So now, why did we do all this? So the reason we do all this, and remember this was our answer from earlier, this is called LU factorization that we're going to solve equations with. All right. All right, so our first thing is we're trying to solve this equation right here. All right, so I'm going to write all these things that are mentioned up here. I'm going to write them over on the side here. So I have AX equals B. I'm trying to solve that equation. So my first thing to do is to know that A is getting changed to L times U, because that's why we're doing our factorization. So I have L times U times X equals B. So this little piece right here, this UX, what we're going to do is we're going to make this an equation. We're going to let UX equal to Y. All right, so that's going to be like a new letter for us. So if I want to solve for, wrong thing. That would be UY. I wrote that wrong. Sorry about that. Erase that. No, I'm sorry. That would be correct. Let UX equals Y. So now when I come back to this problem here, what I now have is I have L times Y equals B. All right, so this is where you can use your calculator. We're going to solve this, this equation by doing this. We're going to basically solve for Y by putting L and B in an augmented matrix, and we're going to solve that out. That'll give us our Y value. All right, and the phone was ringing. Sorry about that. Okay, so then I will know what Y is, and so once I know what Y is, I can come back to this red one right here, and once I know what Y is, I can say that UX equals Y, and I know what Y is, so then I will put U and Y in an augmented matrix and solve that, and it'll give me X. All right, so I know it seems kind of convoluted, but it basically avoids finding an inverse. It just relies on row operations, and so that's what makes it a little bit easier and more programmable. All right, so here we go. And so this problem, if I'm not mistaken, I think is done for us. Yeah, so I'm just going to walk you through it a little bit. All right, So earlier, we have this this problem that we did earlier. We took this and broke it into its L and its U. And so we wanted to use this to solve this problem. So this 2, 2, 3 is given to us now. So there's my original matrix right here. And then this is my original right here. All right, and then that's broken into L and U for later. All right, and so then this part right here is new. So that's our this is like our AX equals B. All right, look at that cool pen. All right, and so this is broken down. So this is what we're going to use right now. So this is where I'm going to break it apart. This piece right here. So that's going to be UX equals Y, and we're going to solve that in a second. All right, so what I have then is I have, I'm going to take my L and my B, we're going to put that in an augmented matrix. So that's what we're doing right here. All right, so there's my L and my B. It's going to be augmented, so there could be like a little line right here, and you could use your calculator to go ahead and solve that, and you would come up with there. So this right here, this answer right that we're getting right there, that is my answer for Y. So, oh, it's written right here. Never mind. All right. So now, remember I had UX was equal to Y. So now all I have to do is take U, my upper matrix, put Y on the side, row reduce it, and get the answer for X. Okay? So that's what's done right here. Right here. And then there's my answer right there, and there's my answer for X. Only done with row operations and no finding inverses. All right, so we're going to do that right here. This problem we had earlier, this is the problem that we row reduced. I think, oh, in example 3. No, this wasn't the one that we did, but it's just actually given to us. So sometimes they're nice. Here's A, and here's the L and the U already given to you there. Okay? And so what we want to do here is we want to solve AX equals B. But we're not going to use inverses. We're just going to use our LU factorization. All right, so here's my L and my U. So just to do this process, all I really have to do is I have to say that A is broken into L and U. There's my X and my B. This is equal to Y, so let UX equals Y. All right. So then I know that I have L times Y because this whole part right here is Y. All right, so I have LY equals B. So we need to take our lower matrix. So our lower matrix, 1, 0, 0, negative 1, 1, 0, negative, I'm sorry, just 2, negative 5, 1. Put that with B. B was the negative 7, 5, 2. Row reduce it, and that'll find my Y. So when I row reduce this, you know, of course, on the left-hand side, it comes out to 1, 0, 0, 0, 1, 0, 0, 0, 1. And on the right side there, on the right, it comes out to negative 7, negative 2, and 6. All right, so this is Y. All right, okay, so then we're going to take that Y value and use it to solve this piece right here. All right, so I'm going to write my upper matrix and put my Y in the augmented part of it, and then row reduce it, or, you know, reduce row echelon and all that, and then we will solve it. Oh, there's another page for me. All right, so now I'm going to take my sorry about that. Let me find it on my paper here. All right. So I got my upper matrix, 3, negative 7, negative 2, 0, negative 2, negative 1, 0, 0, negative 1. Put my Y that I just found, negative 7, negative 2, and 6, right? Row reduce that. And if you put in your calculator, you would get 1, 0, 0, 0, 1, 0, 0, 0, 1. And it will come out to 3, 4, negative 6. Okay, so that right there is X. So you have done this problem without doing any inverses. It's just been row operations and reverse row operations, and that's what we're trying to do. Okay, so the only bad part about this is that sometimes you have to do your LU factorization and you have to do your, if you're trying to do the whole problem, this one was easier for us because we got given the L and the U. So we're going to do one last example and do the whole shebang, and then you have to do example 4 as part of your homework. So notice, it has the LU factorization right here for you already. You just have to do what we just did. All right. And then we're going to do this problem right now. And then when you see example 6 on here, you're going to do this one as part of your homework. So there's your homework right down here. You're going to do these 2 problems in the book, and then you're going to finish 4 and 6. Okay. All right. So if you think you understand what to do here, I mean, you can stop and not watch example 5, but if you want to, whatever you feel like. All right. So let's see. Example 5. So first of all, I have to do my LU factorization. So I'm going to start with my problem. 1, 2, 1, 2, negative 2, 1, negative 1, 1, 1. All right. Remember, I'm going to try to basically get it in echelon form. So I'm going to do negative 2 times row 1 plus row 2. It's going to stay in row 2. And at the same time, I'm just going to do row 1 plus row 3 to stay in row 3. All right, so that 1, 2, 1 is going to stay. This then becomes 0, negative 6, negative 1. And be careful with your operations. This becomes 0, 3, 2. All right, so I think I can basically say this. Let's do half of row 2, add it to row 3, and stay in row 3. All right, so I have 1, 2, 1, 0, negative 6, negative 1, 0, 1, 0, 0. And 3 halves. All right, and that 3 halves, it can stay there or you can get rid of it, but this is fine, actually. So I know that before in our last examples, you had 1s across the diagonal, but you don't really need to. All you just have to make sure is that you got 0s over here and you got your upper triangle right there. Okay, so this is good enough. All right, so let's reverse this. So that was my U. So now I'm going to go and find my L. So I have to take the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Blah. Sorry about that. And I have to do the reverse. So 1/2 row 2 would be basically the reverse of that would be to multiply by negative 1/2 row 2. So negative 1/2 row 2 plus row 3 stays in row 3. All right, so it's going to be 1, 0, 0, 0, 1, 0, and then 0, 0, nope, sorry. That would turn into 0, negative 1/2, and 1. All right, so I got that one. Was this guy right here. Now this guy, I know I was doing row 1 plus row 3, so I'm going to do negative 1, or negative row 1 plus row 3 to stay in row 3. So I have 1, 0, 0, 0, 1, 0, and then I'm going to get negative 1, negative 1/2, and 1. All right, and then the last thing I have to do is this guy right here. I'm just going to do positive 2 times row 1 plus row 2 to stay in row 2. So I'm going to put my answer up in the corner here. So that would be 1, 0, 0. I have my 2, 1, 0, and this is negative 1, negative 1/2, and 1. So it should work out that this is now a lower matrix. So there's my L and there's my U. So basically the quick way to do this is to know the little trick right here. Remember, I have AX equals B. A is broken up into L and U times X equals B. I take UX equal to Y. So then I have LY equals B. So what I'm going to do is solve that. So take your lower and take your B value and go ahead and row reduce that. This will give you Y. So I'm just going to point to the things and show you what I would do. I take my lower. So I'm going to take my lower matrix I just found. I'm going to augment it with B right here. And when I do that and solve it, I will get the answer for y. So when I do that, I end up getting that y equals 8, negative 12, and 1. All right? So once I know y, then I take this part and I say, oh, well, ux equals y. And there's my x coming into play. So I take u, augment it with y, and that'll produce my x. So when I take u is this upper matrix that I made before. I augment it with the y that I just found, and then I solve for x. Okay, and so when I do that, I end up getting x equals, this one's ugly, 32 over 9, 17 over 9, and 2/3. All right, and so you're solving ax equals b, but you're doing it without finding the inverse and all the annoying operations that would come with finding the inverse. And that is it. Sorry this took so long, but it was kind of annoying. So I'll see you later. Bye-bye.